In the previous lesson, we looked at the matrix transposition problem, and we saw that the straightforward algorithm for this problem is not very good if you look at it from the I/O efficiency point of view, because it performs n I/Os, where n is the size of the matrix. So in this lesson, I'm going to explain a different algorithm, which is a cache-aware algorithm, so it needs to know the size of the internal memory, and it's going to perform only n divided by b I/Os. So it's much more I/O efficient. The main idea is to work in what I will call tiles, and tiles are going to be, well, submatrices, parts of this big matrix. So let's see how this works. So I'm going to partition this matrix into these tiles in the following way. Right? You see the tiles are square and they're going to have size t by t. Okay, so first let's see how many tiles do we actually have. Okay, if I've n elements in a row, I've my total number of my total number of tiles would be m over t times m over t. Right, this n divided by t squared. Right? It's obvious we have one tile has size t squared, the whole matrix has size n, so it's n divided by t squared number of tiles. Okay, so this is the way we're going to imagine or look at the matrix. And the main idea is the following. I'm going to choose this t in a clever way, namely such that two tiles together completely fit into the main memory. Why is that good? Well, then what I can do if I have to swap the two elements of one tile, if I have to swap the elements of two tiles, I can read both tiles into the internal memory, fits completely, then swap all the elements, so I'm doing a lot of work without any additional I/Os, because everything now fits in the internal memory. After swapping everything, okay, I write the two tiles back. Okay, so that's the main idea, and let's see again on a simple example how this works. Okay, so here you see the algorithm. I'm going over all pairs of tiles. Actually, as we will see, some pairs actually consist of the same tile, but in general we read a pair of tiles and we swap them. So this is the idea. So first, the algorithm is going to read the two tiles. So initially I is 0 and j is 0. So I have this particular tile t 0, 0. Okay, and here I and j are the same, so this pair is actually one tile. So I'm going to read it into the internal memory, and because of my choice at t, this fits completely. Then I'm going to swap everything as is required when I want to have the transpose. After swapping everything, and this happens in internal memory, I write it back. Okay, then I go to the next pair of tiles, t01 and t10. Okay, together they fit into the internal memory. So I'm going to read everything into the internal memory, swap everything, right? As you see here, I didn't draw all the arrows because it would be a bit cluttered, but all the elements are swapped as they should be to get the transpose. After I've done this, I'm going to write it back to the external memory. Okay, so I'm doing this for all the tiles, read it in, fits completely, swap everything, and write it back. Okay, so this is the algorithm, fairly simple. Now let's have a look at the number of I/Os that it does. Okay, but before we can do that, it's important to look at what this magic number t is. Okay, so remember that the idea was that t is chosen such that two tiles together fit into the internal memory. Okay, so let's have a look at how this works. So how should we choose the tile size? Well, here you see a tile. It has size t by t. And what I want is that, well, on the one hand, two tiles should fit into the internal memory, right? On the other hand, I want to have large tiles. Okay, so why do I want to have large tiles? Well, if I read in two tiles and they are large, I can do lots of swapping before I have to read more tiles. If I had only very small tiles, then it would not buy me much. So I want to have big tiles such that I can do, after reading it, lots of work on them without any IOs before I have to write it back. Okay, so now the question is, how far can I push this? How big can I choose my t? Well, you would say, okay, if I have a tile of size t by t, has size t squared, okay, I want to fit 2 into my internal memory. So in total, I need 2 times t squared, and this should be at most m, right, the size of my internal memory. Well, that's true, but not quite. It's almost true. And so the reason it's not true is, well, if you look a little bit more carefully at what happens when you read one tile, then you will see that the following happens. Right? So here you see a picture of the blocks in one row, and as you see at the end, you have this one block that still sticks out a little bit of the tile. And when I read this particular block, I'm actually going to read stuff which is not in the tile, but in the next tile. So I have to make sure that also these blocks that are sticking out, when I read the tile, I get them automatically. So I have to make sure that they fit as well. And here you see sort of the worst situation that can happen, that on both sides you have almost a complete block sticking out. So on both sides you have b-1 elements sticking out. Okay, so now we can compute how big our t can be. Well, we have t rows, right? It's a t by t submatrix, one tile. Per row I have, well, t elements, plus maybe on both sides b-1 sticking out. So for one tile, I'm going to need, well, t times t plus 2 b-1 number of items. And I wanted to fit 2 tiles into my internal memory, so I need 2 times this number to be at most m. Okay, so that's the value of t that I'm going to use, and well, if you solve this equation, then you will see that this particular value of t, the square root of m over t plus b squared minus b, is the right value. Okay, so this is my t that I'm going to use. Well, of course I should round it because it should be an integer, but this is the t that we're going to use. Okay, now let's have a look at how many IOs the algorithm does. So here you see the algorithm again with the value of t that we were using. And now let's have a look at the IO analysis. So here you see that a number of times we're going to read 2 tiles and write 2 tiles. Okay, well, how many IOs do we need to read or write a tile? Well, per row, I need at most, well, you would normally say if the row has length t, you need t divided by b IOs, but because of these 2 blocks that might be sticking out, you will need at most t divided by b plus 2 IOs. So that's per row. So per tile, I simply multiply by the number of rows, t, and I get the number of IOs to read or write one tile. Okay, so we see that this in total takes 4 times t over b plus 2 number of IOs. Right? And the 4 is because, well, we have 2 tiles. Each tile needs to be read and written. Okay, so that's the number of IOs for one pair of tiles. So now the question is, how many times do I actually read a pair of tiles and swap them? Well, each tile is read once, right? Then swapped with its opposite tile, or maybe for the ones on the diagonal, it's swapped with itself. So the number of tile swaps is simply the number of tiles that we have, well, divided by 2 at most. So this is this number, right? It's n divided by t squared, order n divided by t squared, where n is the total size of the matrix. N is m times m. Okay, so now we can wrap it up. How many IOs did we do per tile swap? Well, 4 times t over b plus 2. How many tile swaps? Well, order n divided by t squared. So in total, we have to multiply these 2, and then we get the following number. Okay, so here you see n divided by b, and that was what I was promising you before, plus n divided by t. Okay, so now what is this n divided by t? Well, let's plug in the value of t that we picked, and then we get exactly what we want. And here, this small technical assumption comes in, which was the tall cache assumption, namely that the memory size, internal memory size m, was at least b squared. And, well, I'm not going to do the computation. You can easily do that on paper yourself. But if you plug this in, you will see that this term n divided by t is actually order n divided by b. So in total, I have n divided by b IOs for this algorithm under the tall cache assumption. Okay, so we have this n divided by b, which is much better than the n that we had for the naive algorithm, right? Because remember, this b is maybe 512, or it's pretty big, so this could be a huge speed up. So we saw that we can come up with an algorithm based on tiles. And this is sort of a strategy that you can employ more often, where you say, well, let me try to read in a lot of stuff and then do much work on this in the internal memory and then write it back. So that's a strategy that sometimes also works for other problems, this tile-based strategy. But of course, it's cache aware, right? Because you need to pick this tile size such that everything fits into the internal memory. And for that, you need to know how big the internal memory actually is. In the next lesson, we're going to look at an algorithm that works slightly differently and that does not need to know the main memory size. So that algorithm is going to be cache oblivious.